The main principle we must understand for this question is the force that keeps the object moving along the circular path, which is also called centripetal force. Unlike typical motion, where the net force and the velocity are in the same direction, for centripetal force, the net force points towards the center of the circle and is perpendicular to the velocity of the object. This is the reason why it moves in a circular motion as shown in this diagram here. The diagram shows a satellite that is moving with some velocity around the Earth, and its force is pointing towards the inside of the circle, which is also perpendicular to the velocity. The formula for centripetal force is shown here, which is force is equal to mv squared over r. One key point about circular motion is that the speed of the object is constant, however the direction is constantly changing, which also means that the velocity is changing. Change in velocity can also be known as acceleration, and this is what centripetal acceleration is. Since the velocity is constantly changing, we can say that the object is accelerating. Acceleration of an object while in circular motion is also known as centripetal acceleration. The formula for centripetal acceleration is shown here as well, and it can be known as acceleration is equal to v squared over r.
In this scenario, we have a motorcycle going up a ring, and we are asked to find the total height of the ring. Here, the total height will equal the diameter of the ring, which is also equal to 2 times the radius. The first thing that we need to do is set up the equation, as shown in step 1. We will use the formula for centripetal force, which is F net is equal to mv squared over r. And when we write out the full equation, we get F net is equal to mv squared over r, which is also equal to the force of gravity plus the normal force. Since the motorcycle is moving at the lowest speed possible, the normal force at the top of the ring will be 0, and we will end up with this equation. When we isolate for r, we end up with this. R is equal to v squared over g, and we will name this equation 1. The problem with this equation is that both radius and velocity are unknown, so we will use the formula for velocity to find the velocity, as shown in step 2. The formula for velocity is displacement over time. The displacement will equal the circumference of the ring, and the time is given in the question. When we simplify this equation, we get v is equal to pi r over 2, and we will name this equation 2. What we do now is we plug equation 2 into equation 1, and we get radius is equal to pi r over 2 squared over g. What we do is we isolate for r, and we get the radius is equal to 4g over pi squared. Once we plug in the numbers and solve for r, we get the radius is equal to 3.97179 meters. In step 4, we need to find the height of the ring. Previously, we mentioned that the height of the ring is equal to 2 times the radius. So we multiply the radius by 2, and we end up with the height of the ring being 8 meters. In this scenario, the normal force of the motorcycle is constantly changing while it is in circular motion. The magnitude of the normal force at the bottom of the ring is at its largest, and as it moves up the ring, the normal force decreases, as shown over here. Once it has reached its highest point on the ring, which is right here, we can see that the normal force is so small that it can count it as 0. And as the motorcycle moves down the ring, the normal force increases until it reaches its maximum once it hits the floor again.
Some limitations that prevented us from obtaining the most accurate height of the ring is that the force of air resistance and friction were neglected. Had they been included, they would have looked something like this in this diagram here, where the red is the force of air resistance and the yellow is the force of friction. However, the force of air resistance and friction would have decreased the value of the speed to drop below the minimum, thus causing the value of the height of the ring to be different.